Yeah, I can tell you briefly something complementary to what I said yesterday.
Once you do that, then we'll make it a broader discussion.
Yeah, so it's basically the same kind of problem. We want to infer interactions from correlations, but with a completely different model. Here, now I want to talk briefly in 10 minutes maybe about the Ising model. So let's forget about neuroscience. It has nothing to do with neuroscience. I mean, ultimately we would like to analyze some data, of course.
So this is the information theory that somebody mentioned yesterday. You already talked about?
Yeah, I mean some approach, maximum
yeah,
entropy.
Maximum entropy.
Yeah, I mean it depends on you. I mean if you're interested or
I think for 10 minutes we're interested.
Yeah.
I can
For
tell
more
you.
than 10.
Yeah, we'll see.
Can tell you briefly.
Yeah, sure.
Okay, so the problem is the following. So let me. So you are given some data. So the data is. So suppose you have a set of n variables. So let's say a system with n variables, okay, which I call sigma I. And so I goes from 1 to n. And these variables are binary variables. So let's say they can be 0 or 1, for instance, -1 plus 1, that doesn't matter. And you are given data, and data are some average values of these variables. So mi, or let's say pi, which is the average value of sigma I, and pij, which is the average value of sigma I, sigma j. So a correlation function. So the average here is taken over, it's an empirical average. It's taken over a set of configurations of the data, for instance. Okay? So going back to the neuroscience motivation, what people do, they have this this raster plot where each dot corresponds to a spike fired at some time for each cell. And what you can do is, if you look, is being the time. Okay? So you want a time being here which is small compared to the typical time between two spikes, so that you never find two spikes of the same cell inside the beam, so that the calling 0, 1 will make sense. And you put a 0 if you don't have a spike, and you put a 1 if you get a spike from this cell. Okay? And since you never find two spikes in the same time, you never lose any information. And the width, so it shouldn't be too large, but it shouldn't be too small, because you want to capture most of the temporal correlation here. And people know how to do that. I mean, you can look at the histogram of delays. I mentioned that yesterday. Typically, time is about, just to give an order of magnitude, 20 minutes ago. It could be 10, it could be 50, but that's the idea. Okay, so you have many time beings like that, and then just do an average, flat average over this time being. So you get some ideas of pi and pij. Okay, so these are your data. Now the question you ask is, can I find an Ising model so a model whose Hamiltonian will be simply minus some over I h I sigma I minus some over ij jij sigma I sigma j, such that the Gibbs average, your average is for the 1 point or 2 point correlation, will be equal to the empirical values. So the question, so as we want, so let me put a E here to say it's an empirical, it comes from the data. So we want to find hi and jij such that the Gibbs average, sigma I, okay, will be equal to Gibbs, will be equal to pi and the sigma I, sigma j Gibbs.
Why the Gibbs average?
Okay, so yeah, okay, so there are two ways of answering the question. So one thing is just do some kind of simple model. So suppose you are given this data, and you want to find a model for the probability of a configuration of the n variables in the same timing. You want to find a model. So the simplest model you can think of would be just an independent cell model. So you try something like that. Okay, call it I. of some probability, I don't know, or rho of a sigma I. Okay?
Yeah, obviously that's very limited.
That's a very bad model. So the next thing you can do is just introduce some interaction between the pairs, right? Okay, and that's it.
Yeah.
So that's the Bayesian way of it. Okay, I'm constructing
Right.
some model, some log,
Right.
likelihood model, okay, for my data, and then I want to fit this function here. And you see, since my variables are only 0 and 1, I can always write this thing, I mean, the log of this probability as such, I mean, in this form. Okay? So that's one way of thinking. Another way is to say, okay.
But I meant it's more like, you know, since you're looking at time averages there, you know, whenever reproducibility is broken, I guess it gives average is not equal to the time average. So hang on, in that sense, but you know, whatever.
Okay, we can talk about that later. So in principle, there is no reproducibility breaking here. I mean, n is finite, okay? Psi is finite, so it will depend on the time. But suppose you have a very long recording, so you have a minimum. But I mean, we can talk about that also. So it's an interesting point. Okay, so another way of saying that is you can say, okay, so that's the maximum entropy way of saying the same thing, which is let's look for the model with maximum entropy, less constrained model, which is able to reproduce this set of constraints. Okay, and then you get that. Okay, where the hi are just Lagrange parameters conjugated to these constraints, and the gij are the same thing for these constraints. Whether actually you should look for a maximum entropy model is another question. Why it should be a good model of data, I don't want to answer this question, but that's a well-defined problem. Okay, so it's a well-defined problem. And actually, this problem has been studied in many different communities, not too much in statistical mechanics. There are some works.
Is this the one that proposed by James in the 100 years ago, like maximum entropy subjected to the constraints?
Yes.
This is the one,
Yes,
right?
exactly. That's exactly its approach. Yes, absolutely.
But
I'm not claiming it's new.
no. I just want to have the connection. But that will assume that this system has the you have a well-defined energy function. I mean, this is a dynamical system, like the neural networks.
Yes.
How do you make sure that you have a Hamiltonian to begin with?
Well, you know, I mean, here I'm assuming that the activity basically is stationary.
Is
Stationary.
I couldn't hear this word.
Stationary.
Oh, stationary. Oh,
Yeah, sorry about it. I'm just assuming that, okay?
well, but the stationary doesn't mean equilibrium.
Oh, no, I understand. But I mean, so you have two ways of stationary, mean that you are looking for probability here where basically this quantity. So when you have all these time beings,
Yeah.
you're assuming that this probability actually doesn't change with time. Okay, that's I understand that's
Yeah,
stationary.
but that still doesn't mean that it's equilibrium. I mean, you can have a steady state, but
Without equilibrium, yeah,
yes,
with fluxes and so on. I agree with that.
Yeah. But,
But-
how do you know? How do you know in this system there's no such a thing? I mean, it is in equilibrium state. I mean, because when you write down Hamiltonian, you already assume it's in the equilibrium state.
Yeah, I mean, I told you to
How do we know? I mean, to begin with. I mean,
How do we know that this kind of hypothesis is a good one?
no. I mean the age.
And this is just implied. I mean,
Yeah, I mean, he's focusing on a certain aspect of the data. If you have a time sequence, you could do lots of other things, but he's just taking the time averages. And this is what you compare it to.
No, I think I have no problem with the first equation. This one I have no problem with.
that's the same thing as this one.
No, but how do you connect the p with the h?
Oh, that's just
The e minus,
that's
just
just
minus log p.
that's just minus log p.
Yeah, that's the. I have some problems with this.
Wait. Okay, so no, I
It's
understand.
just that,
Okay, so you have a set of data.
Yeah.
Okay, so
Yeah.
so what is the assumption here?
Yeah.
So what is a set of data? Again, let me draw it. So that's time, and that's the cell index, okay?
Yeah.
And now we have a discrete time, not just a time being index, okay? So I'll assume it's okay, draw this way. to help this. So here I got, let's say, a discrete quantity which is sigma IT. And what I'm saying is the following thing, is that the probability of sigma IT, so the whole raster plot, the whole set of data, so 0, 1s for each I, each t, will be equal to a product. I'm assuming, that's my likelihood for data, is the product of a t, so that's basically decoupling all the different timings, that's a major assumption, of some probability, sigma I. So here it's a, here it's a for given t, okay? So let me write sigma 1t, sigma 2t, and so on. So that's the first assumption. Okay? Now, second assumption, that's a complicated object, multi-body object. I'm considering only two-body interactions. And then I end up with that.
Yeah, the form is fine, but when you specify this, the sum of hi sigma I, ji sigma j as h, that's the point I'm opposed to. Of course, you can say minus log p is equal to sum of hi sigma I, and you can fit with that. But if you identify that as the h, then you imply that the gradient of which is the dynamics, which is not true.
There is no dynamics here.
Huh?
There is a real neural network dynamics, but in the analysis of data, I'm doing no dynamics. So I shouldn't call it H, I should call it L, the log likelihood.
Then I'll be more happier.
That's not an energy.
Yeah. Okay.
I mean,
It
looks like an energy.
Yeah, that's what I mean.
Okay.
It's not necessarily an energy.
I mean, I just call it H because it
Yeah,
looks like
that's
H.
fine. Okay, all right. I'm fine.
But, so for some visual stimuli, actually this assumption is not a good one. Clearly, it's really driven by stimulus. But for spontaneous activity in some simple cases. But anyway, that's a problem we looked at. So people have been interested in this problem in different communities, so in machine learning, for instance, or in statistics. So I wanted to show, maybe I don't know if you are very interested in the details, but...
how good a result can you get?
Okay, so I can tell you what we have been doing. And, so the question is this one, and actually there is one kind of informal conjecture in the statistics community, saying that basically solving this problem cannot be done in a reasonable time, in a polynomial time, if you are close to a critical point. Okay, and so it's a mathematical statement. Actually, I think the practical there is also a practical version of this statement, which I think might be more interesting for people doing experiments, for instance, and that's related to what we to this thing here. One of the questions is obviously what you are measuring is the activity of a few cells here, or a few components, which are part of a much bigger system. Okay. Now you get some interaction. Suppose you are able to solve this problem. You get some GIJ, so you get some network of interaction here. But if the correlation length of the true system is actually is bigger than the one of the suppose that psi actually correlation length is bigger than the subsystem size, does it make any sense? That means if you had a larger sampling technique, maybe you would see the activity of other cells here, and that would completely change the estimated connection inside. So it's a question, an important question. How is the estimate here? How does it depend on the correlation length? And we don't have any proof of anything, but we think actually that this conjecture is not correct. That you can estimate the J's inside, even if the system here, in some cases, even if the size of the subsystem is smaller than the correlation length.
As long as there's some sort of locality in the component.
Yes, some kind of, yes.
Yeah, okay.
So we have some arguments by that. But if you have a sparse network of because basically the fundamental quantity you are interested in here is so what is a critical point? It's a point where the susceptibilities will have some divergence in the large size limit. So and what is the susceptibility? So I can define, let's say, the susceptibility chi ijk, which will be, let's say, the response of the correlation, for instance, dpij, to a change in the coupling. Okay. I mean, you can do, usually people look at the change of the magnetization, the change in the field, but you can obviously generalize this quantity to 4 in the city, okay? Which is essentially the force spin correlation, okay? Which is measured. Okay, so if you are close to a critical point, this quantity will be long range. That means that if you have your system here, and you are looking at the correlation between I and J, that will be affected by a change in the coupling between K and L very far away. Okay, if you are. But actually, in the inverse problem, this is not the quantity you are interested in. In the inverse problem, you are interested in the inverse of this matrix. So it's a very simple observation of this chi minus 1 and JKL, which is how, suppose you have solved your problem for a set of data, and now suppose you want to change a little bit one observation. You change Pij by some quantity epsilon ij. And you say, oh, okay, so how much do I have to change all my estimates for the interactions, for instance? So it's a response function for the inverse problem, which is the derivative of the Jij, or the JKL, with respect to Pij. And what we claim, and it's just based on a few examples, is that this quantity is actually of a much shorter range than this one. So there are a few results about that. Not too many actually in literature. So there are a few examples in one. So there is a paper by Perkus in '87 where we looked at one-dimensional systems.
Well, it's nice. I mean, we're just giving, we'll just grant that these are like free fields. There should be some immediate.
For free fields, yes, for free fields you can see that. I mean, if the geometry is sparse on basically short range, that's basically JJ, and you see it immediately. But for Ising spins, you know, with interaction, that's not so obvious. But I mean, for instance, consider for instance a critical point for the Ising model, where you know that this will be a. If I consider for instance only the usual susceptibility, okay, something like that. Okay, that in Fourier mode diverges like 1 over Q to minus eta, where eta is a critical exponent. Now, so suppose you, for instance you are in dimension larger than 4, that's 1 over Q squared. Okay? Mean field is correct. Just free field. So that means that the inverse quantity in Fourier mode for space is just Q squared, right? Which is just the Laplacian operator, it's a local one. Obviously, if eta is not equal to 0, that's not anymore a local operator. But still, I mean, you get a parallel decay, which is much, much faster than this one. Okay, there are a few examples in 1 dimensions, and actually it's used also in liquid theory. You know, if you think back of the whole diagrammatic expansions in liquid theory from the 60s, and by a lot of people, we talked to Joel Lebowitz, for instance, and so on, Perkus, and so on. And people, and based on the idea by Einstein and Denker, you know, about the direct correlation function, they express the correlation function between two particles as a sum of some direct correlation plus a mediated quantity through some other particles, which is the definition for the direct correlation. Actually, this direct correlation here is very similar to this chi minus 1. Yeah. And it's used in closure scheme, for instance, for to obtain the equation of states for liquid. It's used at the fact that people assume that this quantity is short range. So for instance, the Perkus-Stedelijk approximation is exactly to say that this direct correlation has the same range as the interaction potential, which would be the diameter of a sphere if you have a just half-speed interaction. Okay? That's not true, exactly, okay? Because at the critical point it's infinite range. But it's a good approximation if you are not too close to the critical point. So certainly it has a shorter range than this one. But we don't have any, quantitative understanding in many
systems. This would probably also be true in the ADS-CFT, right? Because if we just grant that we're expanding some solution, right, and we compute the 2-point function by the linearized fluctuations around the solution, then that's expanding local equations of motion to get the linearized fluctuations. So the statement that those equations of motion are local, right, is more or less the statement that he's making. Right, so you would invert, you would solve the Green's function for those linearized equations to get the top thing as a two-point function. And the statement that is really just coming from solving local equations you get by linearizing around some background is the statement that he's making. Right.
So if this is if this is true, then that means that if you want to infer the coupling somewhere, that shouldn't depend on too many correlations. Okay. So there is no need to have a sample to sample the whole system size. So it's an important point. So we don't have any proof, but I think that's correct.
You repeat again this argument. I didn't hear.
I mean, it's an intuitive argument. I mean, if it is true that this quantity is short range compared to this one, okay, this one defines psi, this correlation length. If the correlation length attached to this quantity is much shorter, then it means that this coupling here, KL, depends only on a few Pij in the vicinity. Okay. So that means that the inverse problem is somewhere is not too hard. So based on this idea, we develop a cluster expansion. Maybe I don't want to enter too many the details. If you're interested in
don't do that.
Okay. So based on this idea, we develop a cluster expansion to basically identify the clusters which are important to do that, and we apply it to data. So this is the and we have a paper a few months ago.
Okay. That's a very interesting point. I mean, we're so used to, as either high energy or cancer physicists who try to infer something about short distance behavior from long distance behavior, which is of course, it can be easy or it can be hard, but it's just much discussed problem. And now basically you're trying to infer this behavior sort of at the same distance here. You're saying just given the measurements at a scale, infer a couple at that scale.
Yes.
And you're saying that that's really an easy problem in a certain sense. So it's this problem that doesn't have to involve interactions with many other scales.
Yes.
Yeah.
So, but
Yeah.
we don't have a mathematical proof. Okay, but
sure.
I think it makes sense.
It's a principle.
Yeah.
It's more interesting. Yeah.
The claim would be that this is true in general for this particular system.
For some, in some generality, for some big classes system.
Yes, when you have
But, I mean,
local
if you
interactions.
compare it to ADS, I think that there, I guess, large N is important
To make that argument,
or like
it's
large
not-
12 cup.
the argument is easy in large and large.
Yes.
Then it might be true in some more.
So here it's not a large. I mean, we have interactions between them.
Well,
you know, I mean,
everything you said is orthogonal. Mr. Eisenhower is not large n, but all the things you said you could have said in large n.
Oh yes.
Yeah.
So for spherical model, for instance, yes.
Yeah.
So for a spherical model, actually, yeah, put that in the paper. Everything can be computed easily. So when you see it. So as long as J is sparse and local, then you will get it. So it doesn't have to be like that in real data. Maybe when we analyze the data, we find a network of interaction J which is not sparse.
Oh yeah, I mean, the brain doesn't have locality in any sense.
Yeah, so that's another question.
It's more of a physics thing.
So yeah, so
Okay.
That's
So, great. And this is a discussion session, so I mean we could try to discuss things related to these topics, or we could there's several other I think interesting things we could discuss.
because yesterday we talked a little bit about your paper.
Right. So we started talking a bit about the landscape.
Yes, and the complexity issues and that. I'd be very happy to hear about that from you.
Okay, I mean, it's all kind of ideas and process of development. I mean, I started talking a bit about people's picture of cosmology in the landscape, eternal inflation and the like. I guess I didn't finish, so I could try to, should I try to now?
Yeah, sure.
So,
maybe I should just
we talked a bit yesterday also about combinatorial optimization and structure of phase transitions in these problems and what's known, but then we moved on to the landscape kind of questions, and so what kind of questions would we have about the BP landscape or some more realistic string theory landscape, and excuse me. Why don't you go on without?
So I saw in the paper that there was some a short section about the spin glasses, and you want to make the connection more precise or more quantitative in some way.
In